Charged particles often repel or attract across empty space without any physical contact. To understand why they move this way, we look to the electrostatic potential, the invisible landscape that governs their acceleration. Imagine pushing a tiny positive test charge from infinitely far away toward another stationary charge. That process requires work. If we take the total work done and divide it by the size of that test charge, we find the electrostatic potential at that specific destination. Because we divide by the amount of charge, the resulting potential, V, is a property of the location itself. Whether you bring in a massive charge or a microscopic one, the work-to-charge ratio at that exact spot in space remains constant. This is similar to water flowing down a terraced hill. Water naturally moves from a point of high elevation to low elevation. In an electric field, a positive charge will move from a region of high electrostatic potential toward a region of lower potential. Just as gravity creates the physical terrain that directs water, the electrostatic potential field provides the structural architecture that guides electrical movement. With the concept established, we can derive the exact math needed to calculate the potential at a specific distance r from a point charge. We calculate the total work by integrating the electrostatic force from infinity to our target distance r. The equation's negative sign accounts for moving the charge inward, opposing the outward electric field. Solving this integral gives our final formula. Potential V equals 1 over 4 pi epsilon naught times source charge Q divided by distance r. This graph compares our potential formula to the electric field. While the electric field decays sharply at a rate of 1 over r squared, the potential curve is more gradual. It follows a 1 over r decay. This difference explains why the direct pushing force of a charge drops off quickly, while the potential energy landscape maintains its influence over a much wider area. Potential is a scalar quantity, meaning it has no physical direction. However, its mathematical sign provides specific information about the forces involved. A positive source charge creates a positive potential, meaning you must exert force to push a test charge inward against repulsion. Conversely, a negative source creates a negative potential. Since the source charge is pulling the test charge in, you must actually pull backward to move it without acceleration. Let's apply this to a specific problem. We have a source charge of 4 times 10 to the negative 7 coulombs. We need to find the potential 9 centimeters away and determine the work required to move a new test charge there. Pause to calculate. We convert 9 centimeters to 0.09 meters and solve for potential, getting 4 times 10 to the 4th volts. Next, multiplying this potential by the new test charge yields a total work of 8 times 10 to the negative 5 joules. Mastering these unit conversions and sign conventions is how we quantify the energy requirements for everything from microscopic circuitry to regional power grids. We just calculated the work for a straight path, but what if the charge followed a winding, chaotic route to reach that same destination? The route has no effect. Work is entirely independent of the path taken. A complex path combines steps parallel or perpendicular to the field. Perpendicular sideways movements cancel out, requiring zero work, leaving only the net radial displacement. For quick revision, remember, potential is work per unit charge, using a 1 over r relationship. And because the field is conservative, work is always path independent. If this helped you visualize the field, like and subscribe for more. In our next session, we'll use these principles to calculate the potential energy of entire systems. Potential provides the structural map for electrical movement, defining how energy is distributed and mobilized within any charged system.